Welcome. Good afternoon to everybody. We are still continuing the spectrochemical methods of analysis, where we are talking about something which we can consider as a titration, and we want to detect that particular titration when we introduce a spectrometer or a spectrophotometer to identify where the titration gives us the corresponding endpoint. So, in case of the typical acid based titrations, where we know visually we can do by corresponding manual titration that both the acid as well as the base, they are colorless. So, we cannot use for this particular titration to detect its endpoint by a spectrometer or a spectrophotometer. So, what should be the solution for that particular purpose? And also sometimes we can see that a complex situation may arise as we are talking about the corresponding titration of a sewage water, where the titration we can perform, where we can have both the bicarbonates as well as the corresponding acids. So, volume of the acids or the amount of the bicarbonates we can go for titration. So, these we can analyze by using a standard sulfuric acid solution. That means, a known solution of sulfuric acid can give rise to that particular acid. So, the corresponding volume of the fatty acid, so this is fatty acid, so mixture of the fatty acid. So, this is after degradation of wastewater. So, at some point we are talking about this thing, but right now what I want to tell you is that how we can move or how we can design or how we can think of a particular titrimetric method with the help of an instrument, because when we introduce a spectrometer, we can call it as a method involving the instrument. So, instrumental method of analysis or chemical analysis. So, that is a huge area of interest, and that can itself be a separate course where we can talk about the corresponding instruments, but in this particular course I will try to introduce some basic aspects of all those instruments and how we can design. If you know what is your problem, because the problem is how you treat the wastewater and how you decompose the wastewater to get two components, and we want to analyze the corresponding concentration of those analytes in terms of the corresponding fatty acid concentration and the bicarbonate concentration. So, when we go for this particular titration using a standard sulfuric acid solution, obviously it is a dilute sulfuric acid solution. So, standard and dilute solution. So, for these two components, so basically we can have two analytes. So, it is a situation where we can consider it as a two analyte situation, where we can go for a titration where the final pH, that means the pH at the neutralization point, can range from 3.5 to 5.1. That means, in the typical acidic region, we can recall back the amount what we have utilized for acetic acid pK value, which is 4.75. So, this particular case, so this one, if we can go for the titration, this will definitely determine the volume of fatty acids. So, this the fatty acid neutralization can give rise to the corresponding endpoint at a pH value of this 3.5 to 5.1. In another case, if we go this particular one, where the pH of the neutralization point can be above 5.2, which can be for your corresponding amount of carbonate present in it, carbonate as well as the bicarbonate. So, this particular one, so whether we can go for a instrumental methods of analysis or a simple manual volumetric acid base analysis, but what we can compare is their results. So, if we compare the results using a spectrophotometer, we will just discuss today only that how we can introduce a instrument and how we visually detect this corresponding endpoints for this titration of these two mixture of the analytes or the components. So, the results, if the results are comparable, we will find that this manual titration is very good and we can go for analyzing this thing, but a continuous analysis or continuous analytical process for this would not be that much feasible for us, because in industry when you have the reactor and reactor is responsible for your wastewater treatment within an anaerobic condition. So, bacterial degradation is producing bicarbonate and fatty acids. So, if we go for a continuous monitoring, so in that particular case it is the instrumental method which will be beneficial, and that instrumental method can give rise some important information. So, what we can do now is that because the spectrometer can detect the lambda max value if it is colored in the visible range, okay, in the visible range. So, to how to get that particular thing is that we will introduce something which we call as a color changing indicator or a colorimetric indicator. So, that particular indicator, which is again a weak organic acid, and that weak organic acid, as we all know now, that it can also remain as the chemical equilibrium what we are talking so far if it gives rise to the liberation of the corresponding proton and the anionic form of that indicator as In minus. And if both of them are in equilibrium, that means since the corresponding Ka value for this would also be the corresponding concentration, that means H plus and In minus and the undissociated weak acid which is HIN. So, in a similar fashion or in a similar way, we will introduce something as a colorimetric indicator which can be a very weak acid and which can go for this dissociation. So, this we all know that this particular one will be related to that particular compound in a medium, say it is aqueous medium or a non-aqueous medium, can have a very characteristic pK value for that molecule and which will be related to that particular pH value. And as we all know, like your acetic acid, the corresponding relationship between the corresponding conjugate base and the free acid. So, in this particular one, if we choose something as the indicator having a characteristic pK value, and that indicator can change its color in a particular pH range. So, this pH range is of interest to us, which will be directly related to the pK value of that basic indicator. And if we see that in one case we get that a particular example of that like weak acid, we will take something we all know about the phenolphthalein and we all using that particular phenolphthalein. But here we will talk about something very much related to that, which is name is phenol, then we will talk as sulfone. So, just remember the name very well. So, because the name will tell you something, that phenol, then sulfone and phthalene. So, this is one such indicator which is related to that of your phenolphthalein, and this particular one, the molecule is nothing but again related to your phenolphthalein molecule, what you have, you can remember it nicely. This is your phenol part. So, we have the phenol and something which is coming from the phthalic acid part or the phthalene part is your this part, and we have this each part over here, and this group when it is SO3 minus, it is the sulfone phthalene, and when it is carboxylic acid, it is your phenolphthalein. Okay. So, by the introduction, why I am talking about this that means sulfonic acid group versus the carboxylic acid group is the fundamental difference is that its corresponding pK value for this acid dissociation constant. These are all weak acid like your acetic acid. So, these are phenol based molecules. So, these phenol based molecules can undergo dissociation and it can have the corresponding color change range. So, the pH range for the color change related to the corresponding pK value. So, if we take, because this can also be experimentally determined quantity, we can determine this pK value of this molecule by knowing the corresponding concentration at different buffered pH values of the medium. So, this pK value is 7.6, and what we get in all these cases, say whenever we get the pK value, there should be some rule that how we can tell about the corresponding color change range. So, the pH range for color change, that means the color for the HIN and IN minus, these two colors will be different. So, in this particular case, this is 6.8 to 8.4. So, when the pH is less than 6.8, the molecule in solution can show its corresponding color in acidic form. That means this form, this is the corresponding phenol form. So, this is the acidic form, and this acidic form has a yellow color. Then this yellow color is for corresponding HIN, if your HIN is present over there, and through deprotonation what happens, it can go to other form which is colored. So, the colored form again SO3 minus unit is there, and this remain as O minus, but this particular one with the removal of this hydroxide group as well as the corresponding phenol is going to a quinone form. This quinone form, you see that more number of these double bonds, the CO double bond and CC double bonds are there. So, there is a conjugation. So, the corresponding absorption in electronic energy can be in the longer wavelength region, that means the low energy region. So, as a result we get this particular compound showing a red color. We call, sometimes we call something that something is red shifted, that means it is going to a longer wavelength range. Since it is going to a longer wavelength range and it is in the red, so this is can be a one of the quinonoid form. So, another resonating form is that this can also be a quinonoid form. So, the relocalization is more between these two rings. So, this red is one of the resonating form. So, one of the resonating form what we get for this. So, we get one is yellow. So, yellow is this one at a pH value of 7 point, and another is red is 8.4. So, we can define in that way what is that particular corresponding indicator for any acid based titration, because we are talking about something where the change is in your H plus concentration. When we talk about the corresponding redox titrations, we will see that the E0 value can also do something related to the oxidized form and the reduced form. Here is the corresponding protonated form, that means the acid version, and the anionic form, that means the corresponding conjugate base giving rise to a different color. So, what we have seen that if you have a Ka value which was your H plus and your In minus, so this will give rise to your Hin, and that basically give rise to the corresponding concentration of this and corresponding concentration of that. So, what we get over there is your Hin, this is your Hin, that is written over there, and this is your In. So, when we do the titration visually, so you have the visual observation for the manual titration. So, visual observation what we get for this is that what is the color of this species and what is the color of that species. So, when they are present mostly at a concentration of 90%, this particular color of this species, that means the yellow color will be dominating over there, and when this is present at 90% of that anionic form, so red color will be dominating. So, that corresponding ratio, that means 10 is to 90% or 1 is to 9%. So, we get that the ratio, this is corresponding, the pH value is in the logarithmic function. So, we get 1 unit change. So, there will be that corresponding pK value for this can give rise to the corresponding color change range, which will be plus minus 1. So, that is why we get a value 1 unit less than the corresponding pK value and 1 unit more than that of your corresponding pK value will be your range for the color change. So, whenever we have a particular compound, we immediately know its corresponding Ka value as well as the pK value, and the indicator range will be there. It can vary, not is going to up to 2 units, it can vary from 1.5 to 2 pH units. So, the color formation what is happening over there we can detect nicely, and all other indicators which are related to this molecule also, because phenolphthalein is related to this particular one. Similarly, another one molecule which is bromocresol. So, this bromocresol green, where we have the substitutions, suppose we can have substitutions, the bromine substitutions at all those positions in this particular ring. What happens then? So, if we have the Beer corresponding Beer groups over here, your Ka value will be changing. So, your pK value will be changing, and since the pK value is changing, your pH will also be a different one. So, that is why this bromocresol grain, like that of your phenol sulfonthalein, can change its color into two. The green itself tells us that you can have a color which is blue green and another one which is similar to that of the previous molecule, which is yellow. So, HIN color for bromocresol green will also be yellow, but the corresponding anionic form, that means the form which is giving you the extended conjugation, that means your energy values are changing in that particular way, which is blue green in color. So, that is why its color change for this particular range is different, and the corresponding pK value is giving something, and its color change pH is from 3.8 to 5.4. You see the change what we can introduce. So, there are several molecules like these, and people are trying for that also, that how you can change the corresponding range from 6.8 to 8.4 to 3.8 to 5.4, because our neutralization point where we have the end point. So, at this particular end point we have the corresponding difference in all these values, where the final pH at the neutralization point neutralization point is different. So, since this particular pH value is different for different acid base combination for this titration, so we have to use different indicators, and that how you know that we can have a corresponding indicator and how you choose the right indicator. So, we must have some good knowledge about the final pH for the end point of a particular titration. So, this pH basically is changing for a considerable range. What we know that the titration curve, if we follow to a low value of pH to a high value crossing that particular end point. So, what we get this corresponding thing for this particular plot against pH, and pH is starting from say 2 to say this is 10, then 12 and 14. So, this particular case when we have a corresponding change in this color. So, when we have this steep rise in this particular titration curve. So, in this titration curve, when there is a steep rise in this change. So, what is that particular pH? We should look at these pH values. So, these pH values are characteristic for this particular titration, which can be a strong acid strong base combination like hydrochloric acid and sodium hydroxide. So, any of those discussed indicators can be used over this to indicate the corresponding sharp end point. But as we all know that if it is not a strong acid strong base combination, what happens that we just go for the rising of this particular part and it is basically not so sharp, that means this particular range is less. If we go for a weak acid strong base combination and finally the weak acid weak base combination. For a weak acid weak base combination, this vertical line, the size of this vertical line is very less. So, we cannot use a good indicator, that is why for this no indicator or available indicator is there, which can be used for this titration where we do not have the steeply rising part of a titration curve. So, what we do that the pH change over a minimum volume of the titrant, because this is the volume of titrant we are adding. So, volume of titrant. So, if this is very sharp, you see this much change in volume. So, this is the change in volume of this only small volume. So, this much small volume change of the added titrant. Since we are talking in terms of a low pH range, that means the acid is in the conical flux and in the burette you have the base. So, when we are adding, so due to the small addition of that particular base, your steep rise in the pH value will take place and it is crossing the corresponding pK value of that particular indicator. So, we know that this particular value, which will be the close to that 6 to 8 value, 6 to 8 if it is there in the 6 to 8 range. So, your phenolphthalein can be a good one. So, you have the indicator range. So, this is the corresponding indicator range for the phenolphthalein, and therefore, phenolphthalein is a good indicator to use for this particular type of titration where we get a sharp end point. Okay. So, this is therefore a very interesting thing to know that how good the plot is, but if we move to a different titration and we know the example for that also is your corresponding value for this one where it is changing from less than 2, it is the pH value of 2 to say 14, Okay. So, in between you have 6 and 10. Okay. So, 6 and 10, but this plot is something broadened and like this, and if we go for this sort of titration, if it is not like this one, is not sharp, and even it is for this particular one, and if we use another indicator which is methyl orange, we abbreviate as MO. So, is methyl orange, if we take orange is related to again its corresponding color, and it has a good azo function which we all discuss once again, which is the chromophore responsible for its color absorption. So, most of these azo compounds or azo molecules are colored. So, this is giving rise to that particular color. So, what we see that in this particular case, even for the strong acid strong base condition or any other one, that means the weak acid strong base combination, weak acid strong base titration, and if your this range is coming over here only, you see this is very much vertical and the horizontal one is very sharp and is not much volume change. So, one drop of this change. So, this change is coming from 1 or 2 drops of this addition for this particular sharp change, but here you see the volume required for this is more. So, this volume, this much volume for the volume of the titrant is much more. So, use of this particular range, which is the corresponding MO range, that means the range for the indicator methyl orange, is not good. Therefore, we label it as a bad to use, because what it can give you that the detection is not very much distinct. Therefore, we can have imprecise or indistinct determination or indication, that means which is indicated. Indicator is indicating your endpoint. So, if it is not very much perfect or not very much right one, we can label it as imprecise or indistinct change in the corresponding pH for its color change. So, this corresponding equivalence point will not be detected nicely, because as per this curve what we get this corresponding actual equivalent point. So, this actual equivalent point we are trying to detect by the use of an indicator where it is changing its color, but you see the difference from this point to that point is only within a range of 1 drop of that particular titrant what is being added. But in these cases it is in this particular case it is not, it can be milliliter. So, this particular milliliter range of error will be crept in if we use methyl orange as the indicator. So, that will not give rise to, or we cannot afford for this particular type of titration, and we will consider this particular one for a indicator error. So, the right choice of that particular indicator is important, and how do we use that particular indicator for this titration is also important. And when we have this, like the previous examples what we are talking earlier, is the mixture. That means, if you have a carbonate mixture and we are trying to determine both carbonate ions and the bicarbonate ions into the mixture, and in that particular case what sort of plot we basically get, because always we should keep in our mind the corresponding titration curve. So, this particular titration curve as we move, so this will be titrated by standard hydrochloric acid solution. So, that particular one when we titrate, and if we see by looking at the corresponding change in the pH values, this is 2 and this is say 5. So, if we get that, and this particular one is not a very sharp one, but is going like this, which is a broad one, and when it is going and moving and up to this particular point is giving a very good change. So, what we get there is that the corresponding volume of this acid what you are adding in milliliter. So, volume of HCl what we are adding in milliliter. So, it is 10 is not showing 0 to 10. So, from 10 how it is changing, and this is basically 20, then 30, then 40, and between 40 and 46 actual values for that. This is 30, this is 20, and this is 40. So, what we see that this particular point what we get over there is your corresponding indicator what we can use. So, this is one indicator range, and this is at the lower pH values. This is another indicator range what we get. So, for all these cases what we can use is your phenolphthalein. So, if we use first phenolphthalein, what will happen? So, phenolphthalein we all know the color change range is close to that of 8, is 7 to 8 in this particular range. So, this is the corresponding range for using pH P, which is your phenolphthalein, and this phenolphthalein can give rise to a corresponding change, but this change in pH, the jump is very small. So, you have a small jump for this pH change, and so you have a slope which is a shallow one. We call it as a shallow slope. Therefore, the detection of that particular point is not sharp, but we can detect anyhow in this particular range. If no other indicator is available, we can use this particular phenolphthalein indicator to detect this particular endpoint, but the most useful one we will discuss afterwards is the corresponding use of the instrument or a potentiometer for the potentiometric titration. But this one is very sharp, and this range as I discussed just now is your range what we all know now. This particular range is useful for your methyl orange. So, if you add the methyl orange you get, and for this combination at this point, this is the midpoint, we get the for the corresponding formation of carbonic acid H2CO3, and that can be detected for a very small addition of hydrochloric acid, a sharp change for this, and the color change is also very much sharp using methyl orange. And here also the corresponding one, the corresponding color, that means pink to colorless situation for the addition of phenolphthalein is in this particular midpoint, is basically we are getting for the formation of HCO3 minus. So, thus we get that this you have the corresponding change. So, phenolphthalein originally when it is in the basic condition, so when you add phenolphthalein the color will be pink, and when it is changing to this particular range is going to more acidic condition, you have the colorless. So, you do not have to bother about the use of multiple indicators. So, this is one such example or a good example for the titration of carbonates or a mixture of carbonate and bicarbonate by hydrochloric acid, such that at one point if you start from higher pH value you can add or you can use indicator like phenolphthalein to detect this particular endpoint. When it is going, you keep on adding this particular one, and when you reach about 30 and 35 milliliter of this addition of this acid, you add now methyl orange. Since the medium is colorless, there is no harm in adding the second indicator to the solution, and we can detect nicely also the corresponding second indicator. So, that is why it is a good example of knowing the use of the indicator and use of the color. Here we have the pink, and here we have the corresponding yellow to red color for this indicator also. the color change. So, if we have 3 color, one is pink, another is the corresponding orange, red, and another is yellow. So, we will see that how the different lambda values will be helpful if we consider, if we try to detect the same titration using any instrumental method for this particular analysis. Okay. Thank you very much.